Over the past decade, the remarkable progress in visual intelligence has largely been fueled by the availability of vast datasets supporting learning, from ImageNet to LAN. Yet, the extensive human involvement in data collection and labeling has inevitably introduced biases. Can we automate large-scale data collection directly from sensors with minimal human intervention? And can models trained on such data generalize effectively to various tasks? Today, depth sensors are ubiquitous, from cutting-edge autonomous driving systems to everyday smartphones, enabling the collection of millions of frames with just a few hours of video. This leads us to pose a hypothesis. Could pre-training on a geometric task yield benefits for downstream semantic tasks? At first glance, this hypothesis seems counterintuitive. Geometric tasks like depth estimation can be performed at the sensor level without requiring high-level abstraction. However, when limited to monocular inputs, the problem becomes intriguing as it necessitates induction. If proven true, this approach could dramatically scale up pre-training data without extensive human labor. We delve into this hypothesis, focusing on monocular depth for pre-training and semantic segmentation for testing. Upon reviewing the literature, we encountered conflicting results, prompting us to investigate further. To our knowledge, despite scattered efforts in this area, we are the first to systematically analyze the problem and elucidate potential underlying mechanisms. We established the theoretical foundations in Section 3, formalizing the problem within the framework of information theory. To test our hypothesis, we explore various network architectures, dataset sizes, and fine-tuning strategies. Remarkably, all our findings support the viability of using monocular depth for pre-training in semantic segmentation tasks. Our investigation extends beyond empirical results to reveal the mechanisms driving this phenomenon. Here we highlight some of them. For instance, we observed a disparity in object scales between pre-training and fine-tuning datasets. To assess the impact of this bias, we conducted cross-resolution experiments, demonstrating that pre-training on higher resolutions facilitates fine-tuning on lower resolutions, but not vice versa. This finding substantiates our conjecture. Furthermore, we explored whether the nature of monocular input is pivotal. By using a Siamese network for optical flow pre-training, we discovered that while depth estimation enhances performance, optical flow impedes it. We attribute this disparity to the ability of depth estimation to capture the stable inductive bias inherent in static scenes. Another intriguing conjecture we explore is that depth maps exhibit piecewise smoothness, facilitating semantic segmentation by assigning labels to these regions. To validate this notion, we trained depth models on randomly cropped patches without spatial awareness, yielding surprising improvements in segmentation accuracy, indicating that depth pre-training extends beyond mere function mapping. Moreover, we examined whether pre-training with monocular depth benefits from training within the same domain as downstream tasks. Leveraging recent advancements in relative depth estimation, we demonstrated consistent performance improvements across multiple datasets, underscoring the robust transferability of depth models to novel domains when trained at scale. While our research marks a significant step forward, it is by no means exhaustive. We hope that our findings will inspire further exploration and spark new avenues of research in this domain. Thank you for your attention.